Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will do our fourth and last video on collisions, and we will treat specifically kinetic energy. What is kinetic energy in the center of mass frame, also how it relates and the different things we can do with it, and the change of kinetic energy when in collisions are inelastic, and how it relates to velocities, etc. So, let's start. Great, let's start exploring how kinetic energy looks in different frames, specifically the center of mass frame. Note that B1 in here equals B1 prime plus B of the center of mass, the velocity of the center of mass. So this relationship also holds for B2 and it's going to be very important. Let's start writing what our velocity would be, our kinetic energy in the initial phase. It will be 1/2 times mass 1 B1I squared plus 1/2 and the mass 2. Now we would like to express this in terms of our velocity in the center of mass and the velocity of the center of mass. So that could be a simple substitution. It's B1 prime plus BZM squared plus, well, this should be vectorial quantities, and we have over here of M2 B2 prime plus the velocity of the center of mass squared. Now what we have over here, and we're just going to assume that they are going to be in one direction only to simplify things, and therefore we can just take the modulus over here because it's not going to influence in anything. So we're going to take these squares with our different expressions, and we will have a first B1 prime, the kinetic energy of this one in the CM frame. Now we're going to have a term that is going to be 2 times 1/2 M1 B1 prime BZM plus the last term, which is 1/2 M1 BZM squared. And we're going to have something pretty similar with the other one, which is going to be the kinetic energy on the first frame, on the CM frame. Now we're going to have a similar term, which I'm going to omit the 2 and the 1/2, and we're just going to have M2 B2 prime BZM, and the last term, once again, the velocity in the center of mass frame. Having this, we can express these two parts. We're going to call them the kinetic energy in the center of mass frame, the initial one. So we have, let's cancel this, and we have covered this term and this term. Now, if you realize, we have over here BZM and BZM, so what we can do is to take a common product out of it, and we get M1 B1 prime plus M2 B2 prime BZM. But note that in this case, this is going to be the total momentum of our particles in the center of mass frame. But by definition, the total momentum of a system of particles in the center of mass frame is going to be equal to 0, as we studied in our multi-particle system series of videos. Therefore, this is just going to be 0, and we can erase that. And our last term is going to depend on these center of mass frame parts, which are going to give us 1/2. Take once again the common product out of this. We have M1 plus M2 BZM squared. And now we have an expression for kinetic energy in the center of mass frame with respect to kinetic energy initial and the velocity of the center of mass. Alright, now that we have a way to relate kinetic energy in any frame to the kinetic energy in the center of mass frame, it would be very useful to find some simple expression that relates kinetic energy in the center of mass frame with the different variables we have. To do this, what we're going to use is the formulas we derived in a previous video about collisions. And we're going to input them in our formula for the kinetic energy in the center of mass frame, and we will arrive to a very simple form. If we substitute them in, what we find is that we have 1/2 m1 b1 prime squared plus 1/2 m2 b2 prime squared. Now by inputting those formulas in, we'll find this is m1 mu squared m1 squared b12 squared, and over here, as it's squared, we're not going to care about the minus sign, and we're going to add a very similar expression, m2 mu squared m2 squared and b12 squared. Recall also that 1 over mu was defined to be 1 over m1 plus 1 over m2. This is what we call the reduced mass of the system, and it's pretty useful when dealing with systems of two particles to make some simplifications. Having this, we see that we can make some cancellations, the m1 with the m1 and the m2 with the m2, and we can take a very big common product out of it. 1/2 the mu squared and the b12 squared can be taken out, and we find this to be 1/2 mu squared b12 squared times 1 over m1 plus 1 over m2. And we see that this by definition equals 1 over mu. Therefore, we can cancel this with one of our mu's. And we find a very simple expression for our kinetic energy. The kinetic energy in the center of mass frame equals 1/2 times the reduced mass times the relative velocity of the system squared. And with this, we can find the kinetic energy using the previous formula for every single frame. Alright, now let's try and understand the different changes in kinetic energy in different collisions by using this intuition we have got from the kinetic energy in the center of mass frame. The first thing you have to realize is that this term is constant before and after the collision. Therefore, the change in kinetic energy in any frame, the ground frame for example, equals the change in kinetic energy in the center of mass frame in every situation. You can realize that in elastic collisions, in which the only thing that happens is that the b12 changes sign, the relative velocity changes sign, the kinetic energy is going to be the same before and after, because there's a square over here and there's not going to be any change. However, in inelastic collisions, if you think about them, when the two objects collide and they cross with each other and stay together, in the center of mass frame, we're going to have a zero kinetic energy in the end. And we can use that to our advantage to find the kinetic energy in every frame. So this would be, in an inelastic collision, total inelastic, the final one minus the initial. All of it in the center of mass frame. And knowing that this one is 0, because they stay crushed together and they are not moving in the center of mass frame, we get that the change is equal to this expression. And if we equate that, the change in kinetic energy in any frame equals minus 1/2 times the reduced mass, which we can express in terms of our common masses, times the relative velocity squared. And this is the last equation we needed to solve completely the different inelastic, totally inelastic collision systems. That is all for today. I hope you understood everything and that now you have more clearer the events that happen in a collision by looking at it through this kinetic energy view. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!